Yes.
Yep, recording.
Okay, I'm gonna let everybody in. Hey everybody, how's it going?
Can you guys hear us okay?
Alrighty, we're gonna wait for maybe 1 or 2 more minutes, and then we're gonna go ahead and get started. If you haven't already, please you can use this QR code or look at the link that was provided on the live site and get access to our GitHub repository with the Jupyter notebooks for today. You're also going to want to get started if you don't already have Python installed and some of the dependencies we're going to be using today. You're also going to want to get those installed. We'll go over how to install them, but if you already kind of know what you're doing, this would be a good opportunity to get that installed. We're going to be using PyTorch today. I don't know if anyone's familiar with that, but that's what we're going to be using today.
If I start talking, it still shows Patrick's screen, correct?
Yep.
Cool.
Awesome. Okay. I think I'll wait 2 more minutes and then we'll get started. But like I said, use the QR code, get access to the repository, and you can start installing some of the dependencies, because I do know that some of them take a while to install. So you might want to hop on that preemptively. Has everyone been enjoying the event so far? Oh yeah, Daniel, it can be any version above 3.0, I'm pretty sure will work. The most recent's probably going to give you the least amount of headaches, but none of this code should be dependent on anything as long as you're using Python 3.
Yeah, I think we're using 3 to 3.6. I don't recall.
Yeah.
Three 7 for me, but shouldn't matter.
Yeah. Alrighty, I think we've pretty much grabbed everyone who's going to come in, and then hopefully more people pop in. It won't be too bad. So with that being said, let's get started. All right, my name is Patrick, and I'm joined here by Andrew, and we're both organizers here at VTHacks. And today we're going to be giving you a brief introduction to reinforcement learning. Don't get worried, we're not going to be going too deeply into the math behind it, but we're going to provide some resources at the end. But if you are one of those people who's a little more mathematically inclined, where you can read the paper that's the basis for our algorithm and how to implement it yourself, and kind of some further steps with using reinforcement learning and some of the tools that we use today.
Yeah, quick question before we get started. Has anyone here heard of reinforcement learning, or have you heard of, say, AlphaGo or OpenAI 5 or anything like that?
Or DeepMind, really.
Yeah. DeepMind in general. Cool, we got 1.
Awesome. Awesome.
And 2. Cool, so I think let's get going, Patrick.
Cool. All right, so this is our plan for today. It's pretty simple. We're really just kind of doing an introduction here. We're going to be implementing deep Q learning, which is a particular type of reinforcement learning algorithm, and we'll go a little bit more into that in a little later. We're going to be using something called PyTorch, which is a framework for machine learning that allows you to kind of do those big fat calculus calculations and updating the network really easily. Does it really, really well, and lets you focus less on the math behind it and more on how you're designing your models. And then after that, we'll be using PyTorch to solve a short little game that's in OpenAI Gym, and we'll show you what the game looks like. And basically, after that, we'll be suggesting you a couple more steps for future learning, and then take any questions you guys might have.
So reinforcement learning is a kind of machine learning that deals with maximizing some kind of reward by choosing actions to take in an environment. So generally, a system like that has an agent, and that agent takes actions in an environment, and it receives rewards for those actions, and then it basically updates itself to maximize that reward. So can we go to the next slide? Yeah, so in old school RL, you basically have a table that you put into the table basically every state you've experienced. A state could be like a frame from a video game or something like that. Think of Pong was the classic example. Think of it as just a screenshot of a Pong game. So you store every state and the actions that you've experienced that you've taken while in that state, and then when you get to that state again, you take the action that had the highest reward for that state. So this is great for really, really small problems. It doesn't scale very well. So ideally, we'd have some way to approximate the value of unseen states and actions based on similar ones we've seen in the past. So if you've seen something that's maybe a pixel away from another state, an old school algorithm would count those as two different states. You would want those to be the same. So deep learning is exactly how we do that. Neural networks approximate functions. Basically, you give it basically a bunch of pairs of some function, some value x, and then some function f of x, and it'll take a guess at what f of x is. Then it looks at what f of x actually was, updates itself. I don't want to go too in depth about that, but if we have any questions, I'll be happy to answer them. So for the RL algorithm we're going to study, the function is called Q of S of and A, where S is the state and A is the action. And Q of S of A is the reward received when the action A is taken in state S. And we're trying to we're trying to refine that function so it gives us accurate values. And then we can choose the action that has the best reward.
So these are some of the tools you need. I know I kind of addressed this earlier, but kind of any Python distribution above 3.0. And then we're going to be using a Jupyter notebook, which is a really cool tool for doing prototyping or quick experimentation with Python code. We use it a lot. Andrew and I have both used it in our jobs, working as interns and part-time software engineers. And it's really useful when you're trying to get something down really quick, but also it makes testing it very easy because you can kind of divide your code up into blocks. We're also going to be using Gym, or otherwise known as OpenAI Gym, which is going to be what provides us the actual environment. I'm going to switch over really quick to our quick notebook. And GitHub is really nice because it allows you to basically see it right there. I don't know if everybody can see. Can everybody see my screen still? Yeah, so if you can't see my screen, please let me know. But this is what we're going to be solving today, and it's called cart pull, and it's one of the classic reinforcement learning problems. Or I guess it's a basic game that we're able to solve using deep reinforcement learning. And the object of the game is to basically get the cart to be able to balance the pull up and down for as long as possible. And where Andrew was talking about the states earlier, for this game, the state is basically you're going to be getting the position of the pull, so how far it's tilted and which way, whether it's tilted to the left or to the right. And that's going to be your input to the model. And then the agent is going to take a discrete number of actions. And discrete just means that you're not going to be applying like some infinite number of decimals. It's basically either it's going to move it to the left or it's going to move it to the right.
Quick note on that environment. You could solve that mathematically much faster than DeepRL would do it. However, it's a great example because it will train for us like in the time we have here. You could plug this algorithm into an Atari game. Those are included in OpenAI Gym. and it would train still. It would just take a lot longer.
Yeah, so today in the notebook that we provided you all, if you go to the one that's labeled, it's this one. It's the one that's for the attendee. We have both the completely solved version of the notebook that you can just run yourself right away as long as you have the dependencies, or we have the version here where we're going to be filling in code, and that's what we're going to be going along with today. Because the goal of today is to kind of get you guys to understand how the process of how a model takes a state and then improves itself over a period of time by playing the game over and over and over again. Like it says here, we really don't expect you guys to get all of these right. It's a pretty complicated process understanding how all these things work together. But really the point is to get you to think about the material instead of just reading it and having it in front of you, because there are definitely studies that show that interacting with material allows you to retain it much better than simply just hearing it, somebody just speak it to you. If you've never used Jupyter Notebooks, you can run each cell individually or all at once. And basically what we're going to do is we're going to give you a couple of spots in our code where we're going to want you guys to fill in. We'll give you a description of what needs to happen, give you guys a couple of minutes to fill in the code, and then we'll give you the solution afterwards and kind of explain a little bit why it happens. So let's go.
So
the first thing,
Patrick, we should pause here and wait till everyone's got it installed, right?
Yeah. So if you are ready to go, just let us know in the chat. We'll pause for a couple minutes while everybody's getting that done. I know PyTorch, depending on your internet connection, can take quite a while. So it's okay if you can't follow along today. These slides are also going to be recorded and uploaded to our YouTube channel. So if for some reason you can't get things downloaded in the time we have, I'm sorry I didn't get you guys. I didn't get that out to you earlier in terms of dependencies. That's my mistake. But if you want to follow along later after you have the dependencies installed, you can always go to our YouTube channel and you'll be able to rewatch this recording as many times as you want and kind of pause and go at your own pace once you have everything installed. So if you got, and Andrew just put in the chat the command you'd want to run. So once you clone the Git repository, and if you have problems with that, let us know. But once you clone the Git repository and go into the directory, you can run pip install -r requirements.txt, and it will install the latest versions of all the packages that we mentioned here for you.
And then once you have that stuff installed, you just stay in the same directory and you type Jupyter Notebook, and it will pop up in a web browser.
Yeah.
So let's wait till a couple people confirm that they have that working.
We'll wait for a couple minutes.
Yeah, and we can answer questions too.
Mm-hmm. And feel free, if you'd like to ask questions via voice rather than chat, feel free to unmute yourselves and go ahead. So Daniel, is it an issue? What command is it running where the script is saying it's not in the path? Is that pip install, or is it the Jupyter Notebook command? Okay.
Are you in the same directory as the requirements.txt file? That should be in the Git repo. Can you send the whole error in the chat? Out of curiosity, Daniel, what happens if you type Jupyter Notebook right now? That error is from pip install, right? Gotcha. Let us know when that's done.
So this is usually an issue of either Python being installed for the user and it's trying to run it from a global context where you're installed it for the user, or pip being installed for the user and it's not installed in a global context. So it doesn't have the ability to actually modify your path. Or it's never had to modify your path before. And so that could be one of the issues. It's why if you're ever really serious getting into Python development on Windows, I really recommend Conda, Conda. It's a great way to manage packages and utilities, and you can make it's a lot easier to manage also Python distributions and everything like that. There's also things like Poetry or pipenv, and they're basically ways to manage packages, so that way you don't have to install them globally. For today, we just figured it'd be the easiest just to install it on your local system. But if you guys have questions about kind of Python development or virtual environments, let us know after the talk, and we'd be more than happy to help you out with that. Is anyone else having any other difficulties, or anyone else still installing right now? All right, so while some of you guys are waiting for that to download, I can explain a little bit about some of the features you're going to see in the file. So the first thing you're going to notice when you walk into the Jupyter Notebook is there's a little section we call hyperparameters. And these are the things that control some of the higher level aspects of a model. And these are often what you'll modify to improve your model's performance once you know that it runs. By changing these values, you can often increase your training speed dramatically. Or if you choose them incorrectly, it can often decrease your training speed and efficiency quite rapidly as well. So there's a whole science behind just picking these numbers, not even picking the actual parts of the model itself. Sorry. I don't know why that's so these are given the same names that we give them in the Python file, or in the Jupyter Notebook, excuse me. So the first one is epsilon, and we're going to go over how each of these are used later on in the code, so don't get too worried about them now. I'm just going to kind of give a little quick overview. So epsilon is the first one you're going to see, and that's going to control the exploration versus exploitation balance as we train, which may sound like Greek, funny enough, but basically allows our agent to explore the space better and escape being kind of trapped in a rabbit hole where it's just doing the same thing over and over again, and it doesn't know that there might be a better solution out there. Gamma is the reward discount factor, so that more recent events are considered more important, because the way a Q network learns is by comparing the prediction of your future reward against the reality of what your future reward was. And so what this does is basically says that more recent events that gave you a reward, whether positive or negative, are more important than events further away. Because if you think about something like weather prediction, or like meteorology, the prediction for the next couple hours is probably going to be pretty accurate because they know a lot of variables and there's not a lot of things that can change. There's not as many variables that can change rapidly within that time period. But if you look at a forecast for a week out, it might be totally wrong. And we expect that from the model. We don't expect the model to be absolutely perfect, predicting things way in the future. So we want to emphasize being able to predict the next few states versus being able to predict something 100 or 200 states in the future, or whatever number might be. Just like how weather prediction, you'd want to be able to predict the next few days of weather, not necessarily 2 months from now, because there's just too many variables that come into play for you to be able to ever accurately model what's going to happen. Tau is an update to the target network. Now, target networks are something specific to a DQN, which is the algorithm we're doing, And basically this just determines how rapidly the network updates. I don't know if you guys have ever heard the analogy for machine learning, like it being a ball in a valley and you're trying to roll, basically you're trying to find the bottom of the hill. And that's what taking the gradient descent in a nutshell basically just allows you to find the local minimum, or in our case, the local maximum score. So what we want to do is we don't want to move in really, really big steps, because then you're just going to keep swinging back and forth around where your desired point is, and you're never actually going to get to the bottom. So by using a target network, you're able to make the network update much less frequently, which will increase training time, but will also make it much more efficient. It means that if you get one bad state or something totally random happened that was like a 1 in a million fluke, it's not going to totally destroy your training performance. And with that comes the batch size. We're gonna go over what the replay buffer is later on, but basically batch size is how many states, actions, and rewards to look at as you update the model. And yes, like Peter mentioned, stability really is the goal, because you don't want a model that it might learn really quickly, but if it's presented with something that's a little bit different than what it might just learn, might have learned training, it will be totally wrong. So you really want to find a model. Really, your goal is to have a model learn to be both stable and effective when it's predicting. All right, Daniel, I'm sorry you're having trouble with the stuff. If you'd like to still follow along now and then watch it again later as you try to implement it, feel free. But again, that's my apologies on things not being able to install correctly.
Oh, so you can ping either Patrick or I in the Discord after this is over, and we will help.
Yeah,
if you want to do this then.
Yeah. And so the final one is the maximum number of episodes, and that's simply just how many games that you want to play during your training session. And so the Q network, like I described, is, as Andrew described, the deep part of it is approximating a function that takes the state and action, the state of the game, and an action as its input, and then it outputs the expected reward based on that state in the given action. We really only give, in our implementation, we only actually give the network the state, and it outputs a vector of rewards for all possible actions and then chooses the one that's the highest. So it'll choose whatever action has the highest expected, kind of the expected reward is the highest, or the biggest reward is the highest. And so the nice thing about PyTorch, if you look at our code here, is that it makes creating a model very, very easy. As you can see, it's less than probably 20 lines of code, and it's simply just creating a bunch of layers and some activation functions. You're probably wondering what those things are. And so basically there's a couple different types of layers. A linear layer is one of the most basic types for machine learning, not just reinforcement learning. And basically that just means that all of the nodes in the layer are fully connected to the next node, to the next layer. And so that means all the information from one layer is transmitted to the next one. And then the activation functions, which you can see in between, those allow us to learn nonlinear functions, which basically means that you don't just have to have like a quadratic equation or something like that. If it's something that's really hard to approximate, using activation functions allows you to kind of approximate a function that would otherwise be very, very difficult to approximate. And the forward function is basically what gets called when we call that Q of S, we're calling the forward function in our notebook. And so and then the next part is the replay buffer. You guys really don't have to worry about too much about this. It's basically just a fancy list that allows us to randomly sample. It's not anything crazy. The only thing I'm going to explain is that the done state might be a little confusing. And that's basically just a 0 or a 1 indicating whether or not at that state the agent won or lost. And if it's a 1, that means the game's over, and and in the next state you see a restart of the game. And that just kind of helps with forming the reward calculation, because if it's the end of the state, if it's the end, then you're going to know that there's going to be a reward. If it's not the end, then there's not going to be a reward. And so probably the first confusing part is exploration. And you're probably wondering, well, why do I need to explore before I even start training the model? And for a lot of machine learning, you wouldn't need to necessarily do this. But because of the way reinforcement learning works, you can kind of think of it as if you're in a maze, giving yourself time to kind of run around the maze and understand where the different turns are before you even consider how to solve the maze. It's being able to see more of the maze from a top level perspective before you try to solve it. And so the way this works is basically it gives some more states in the replay buffer for us to sample from, and we'll go over more over that in the update section. But It's basically your agent for a certain number of time step is just taking random actions inside the environment to just explore, just to find random things to do, and find different states that exist so that when you're trying to predict something in the future, you have more states to sample from.
If I can interject with some theory real quick here,
Yeah.
there are two kinds of deep reinforcement learning algorithms. There's on policy and there's off policy. So with on policy, you basically move in the environment for a couple of time steps. You collect the state's actions, rewards, dones, whatever from those time steps. You learn from those, then you discard them. Then you take a couple more steps, collect the new ones, learn from them, discard, repeat, etc. In off policy, which is what this algorithm is, you save all of the state's actions, rewards, etc. that you've experienced because the model can learn from ones that have happened a long time ago. You don't care whether those transitions, as they're called, were generated with the current version of the model. They can be from any version of the model, including a version of the model that's just completely random, which is why exploration is helpful. You can't explore with on policy. That's all I got there, Patrick.
So Andrew, you can go. I guess you can go ahead and take the update step.
Sure. So the update step corresponds to a little bit in the code that hopefully you can look at while I'm talking about this. Essentially, it's where the Q network improves itself. You get the batch of those states, actions, rewards, next states, and masks that I've mentioned. And you take the reward, and then the Q network's estimate of the potential reward from the next state. So the reward from the current state plus the potential reward from the next state. And that's your target. That's what you're trying to have the Q network estimate if you give it the current state. So you sum those two, and then you calculate the loss between that and the Q estimates, the Q network's estimate for the reward for the current state. And then you basically calculate the loss between those two and update the weights of the neural network. That's handled by PyTorch. You don't really have to think about it. It's just a dot backward, basically, in the code. Then you update the target network, which we don't really even know what that does. It's just for stability purposes. Patrick kind of touched on that earlier. I feel like that step is kind of key, and I might not have explained it super well. So if you have any questions, please just ask in chat. Okay, I'm going to take that as a no. Okay, so this is the first part where we want you guys to write code. I don't know if many of you actually have the notebook up. Seems like you don't, but you can at least think about this, and then we'll show you the solution. So the line we want you to write defines a variable called y. You can look at it in the code, the last line of that screenshot there. There's a y equals fill-in code here. So y is calculated from the data that we sampled from the replay buffer. And we want to train the Q network to predict y. I talked about y in the last slide. I didn't call it y, which I probably should have. But if the game is over, y is rewards just for the current state. If the game is not over, y is the rewards plus the discount factor, which is that variable gamma that discounts future rewards times those anticipated future rewards as calculated by the Q network. So it's kind of weird because you're using the Q network's estimate to update the Q network, but you're also factoring in the current rewards. So it's a little confusing. And a little note there is that the M variable, you can see it on the second line of this screenshot right there. Those variables are 0 if there are no further steps, and 1 if there are further steps. So just think about how you would write that y equals line of code. I presented it as kind of like an if else, but keep in mind using that M, you can write it without that. So I'm just going to let you guys think about that for like 5 minutes, or ask any questions or whatever. And all the variables that you use are defined right there in that screenshot. So you can kind of figure it out from context.
Except for gamma, but that's,
oh yeah, true.
Yeah, the discount factor. I'll give you a hint that the discount factor is gamma, and it says so on the slides there.
Yeah, I think it's usually set to like 0.99 or something like that, so you could just throw 0.99 in there if you felt like it. But So did anyone think about this? Does anyone have a guess that you want to throw in chat, or just say I have a guess, just so I know that I can move on? Any sort of confirmation? Okay, cool. Let's just move on. And Peter is correct. It's not S2. He's almost correct. It's max next Q, which is defined by calling the Q network with S2 as the argument. So right there in that, look, the fourth line of code there. It says Q target instead of Q. It has to do with the target network. Ignore it. It's not really important right now. But let's try the next one. So this one, I give you the entire formula right here. You just kind of have to look up how to do this in PyTorch. So essentially, to evaluate how good of an estimate for y the Q estimates variable is, or how close together they are, you need to compute the mean squared error. If Q estimates is close to y, the mean squared error loss will be low. So the formula for mean squared error is right there. Essentially, you just, for every element of Q estimates and y, you take the difference between them, you square that difference, and then you take the average of all the differences. There are PyTorch functions. So the Q estimates in y are tensors. So it's kind of like a matrix or a vector or something like that. So every element 0 in Q estimates directly corresponds to element 0 in the tensor, in the y tensor. So if you just subtract those two, subtract Q estimates from y, square the difference with the function that I'm telling you is right there on the slide, and then take the mean with the other function that's right there on the slide. You can calculate that loss. So again, I'll give you guys a couple minutes just to think about that, let it marinate. Post in the chat if you think you have it, or if you just want to say, I think I have it, that's also fine. You don't have to actually say what you guessed. Yes, thank you, Peter.
Yeah. Also, mean squared error isn't something exclusive to machine learning or even reinforcement learning. I'm pretty sure you can also use it in something like linear regression if any of you are statistically inclined.
It will show up in a second semester stat course, or a second semester stat course.
Actually, and if I don't know how many of you guys go to Virginia Tech, but if you take linear algebra, if you're a computer science student and you take linear algebra, you also do a little bit of linear regression at the end of the year, or at least I did at the end of the year in my class, and you use mean squared error to kind of find that optimal value. The application's a little bit different, but still basically the same thing. You're just trying to find what the average. It's basically a way of finding the average squared error. Yeah. So like Andrew said, if anybody has a guess or even wants to say, they don't even have to say what the guess is, but just kind of raise your hand or give a thumbs up or something else to indicate that we're ready to move on, and then we can go ahead and move on to the solution for this.
Yeah. We should like queue up the Jeopardy soundtrack right now.
Yeah.
Like I said, use the PyTorch docs, or don't. Just use the functions I gave you on the screen. Either is perfectly fine.
Yeah. We'll give another minute. Yeah, go ahead, Andrew.
I said I should clarify for dot mean. Dot mean is something you call on a tensor. So if you have a tensor that's like a different squared, we'll call it, you do different squared dot mean, and that computes the mean of all the different elements of different squared.
Yeah.
And you could specify the dimension that happens across, but you don't need to for this application. I'll tell you that now.
Does anybody want to give a thumbs up just if they're ready to move on? Doesn't matter if you've got a solution or not, and then we can go ahead and keep moving. Alrighty, we got a thumb. So solution, there you go.
Yeah. That's about what I kind of described it would be. You take the difference, you take that, you square it, which is what the torch.power bit does, and then you take the mean of all the elements, and that gives you the loss, the average loss, the average mean squared error loss. You could also use PyTorch's mean squared error loss function. That was what we originally had in the code, but I took it out to make it harder. But yeah.
So training is kind of where we're going to pull all the things that we've talked about already today together into one big, in really simple terms, basically one big while loop. And that's how you describe it. And it's basically, it's where the model uses all the things that we've talked about and actually learns, quote unquote, how to play a game. So the first step of training is for this algorithm in particular, it's to explore. And you're gonna explore for a certain number of time steps, and that's just gonna get the agent a bunch of states that it can store and use later in its updating. So it's not just starting off fresh right away. You're gonna loop for a certain number of games, and you're gonna play the game basically until you lose or the game ends because it has some sort of time limit restriction or a score restriction. And then at each step or each state actually in the game, which is going to be part of an individual game, you're either going to take the action recommended by the network or you're going to take a random one. And that's what we were talking about with the epsilon variable earlier, is that depending on what value you set, it'll either be that means that's the likelihood of you picking a random value. And then you're going to record the action you took, the state, the reward, and the next state, all that info into the replay buffer, and then repeat. After each game, or whenever each game concludes, you're going to update your network as previously described, and that's it. You basically just run that for a long time, and eventually the network will learn to be able to play the game.
In theory.
Hopefully.
Yeah. So for the training code, there are two things that I would want you guys to think about before we show you what the code is. So this is the part where we pick the action that the network takes. So there are two possible cases, and they're determined randomly. So some percentage of the time you want to do the exploration, and some percentage of the time you want to do the greedy case, which is where you do what the network thinks is best. In the exploration case, you just do something completely random, and that's so that you can explore more parts of the state. Because if the network finds something that thinks is good, it will just do that all the time, and you'll never find something that's better. So that's why exploration is a thing. But here we go. So the first part is if you look at the code, there's an if random.random is less than epsilon, and there's an a equals blank. That's what we want you to look at. So for the exploration case, you want to figure out how to get an action randomly. There are two ways to do that. You can call a built-in open action method that you can get from looking at the explorer function that we already wrote. You can just scroll up and find that. Or you can use PyTorch's built-in random features to randomly set A to either 1 or 0, because there are two actions here, move right and move left, and one of them is 1 and the other one's 0. So the greedy case, you want to give the neural network the input that it expects. That I'll tell you right now, it's the state, and it will output a vector with 2 dimensions. One of them represents 0, one of them represents 1, or it represents the expected reward for taking the action 0, the expected reward for taking the action 1. And you want to take whichever one of those is higher and set A to that value. So if the 0th dimension is higher, set A to 0. The 1th dimension is higher, you set A to 1. So I'll give you a second to think about this, and then we'll show you the solution.
Yeah, I think we're going to move a little bit quicker. I'm not sure if anybody's following along and wants us to keep going slow, let us know. Yeah. But otherwise, we're going to move a little bit quicker. And then if you're one of those people who's waiting for it to install, again, my apologies, but you can watch this lecture, you can watch this workshop again on YouTube and follow along at your own pace. And again, we'll be here until the event's over. So feel free to reach out to either of us with some questions, or if you want to look for something else for further implementation or further resources, feel free to reach out to either of us. So we'll just give this about a minute, and then we'll show you guys the solution.
Patrick, can we create a channel in the Discord for this, for follow-ups?
I think we'll just have people, if there's enough people who want to do it, we'll do it. But otherwise, you can just feel free to message either of us directly, or just message and ask an organizer, or like mentor help, either whatever is most convenient for you guys. And
cool.
Yeah,
thanks,
Peter mentioned, ask a mentor, and then you can just add either of us directly, and we'll be able to help you out. All right, so here's the solution.
Okay, so for the explore case, you can do env.action space, which gives you the list of possible actions, and then .sample, which chooses one randomly. If you wanted to do that with just built-in PyTorch function or built-in Python functions, you could do a random.random, which will give you a value between 0 and 1, and then just if that's over 0.5, or if it's under 0.5, set it to 0. If it's over 0.5, set it to 1. There are lots of ways to do that, but that's just one. You could also just do Python has a random int method. Just do that. And the second case is the more interesting one. You call Q of S, which gets the rewards for each state, and then you do numpy.argmax. And argmax essentially just returns the index that has the highest value. So the Q of S, that will return something with two dimensions, and then you pick the one that has the higher value, and you set that equal to A. That's all there is for that.
Alrighty, so we have another thing here.
Yeah.
And this is, so this is taking a step in the environment. And you're gonna have to find somewhere that we've done this already. Hint, hint, look at the explore step. And basically this is gonna produce a new state. What it's gonna do is, this is the part that actually controls the cart, and for example, the cart that has the hole on it, and tells it whether to move left or move right. And based on whatever action you give it, it's either gonna move left or move right. And so this is gonna produce a new state based on what happened after you move left or move right. It's gonna produce a reward for that action. And oftentimes the reward is nothing, because in one of the key things that reinforcement learning tries to solve is situations where there are very sparse rewards. So where it's often difficult to figure out whether you did something good or something bad. For example, the Atari games that were originally solved, the only reward the agent got was whether it won the game or lost the game. And that's all it needed to know to eventually learn how to play it. Now that took a lot longer because it didn't know whether individual actions were better or worse, but it still meant it was able to solve it. And that's something that reinforcement learning is particularly suited for, is able to learn in situations where you don't have a lot of information on an individual basis. And so basically this is just going to do, what this is going to produce is a state, a reward, and whether or not the game is done, the doneness or mask that we talked about earlier. And you can discard the info. And then the next state is called S2. And you can return multiple outputs in Python if you're not familiar. And basically we want to stave all of those variables.
Cool. So we can give the shortest amount of time for this one because it's not very interesting. It's just scroll up and look at it, I guess.
Yeah.
But yeah, there it is. Env.step, pass the action into the step function, cast it to an integer, and you get the next state, which is S2, the reward, and the Boolean that represents whether it's done or not. So yeah, that's that.
Yeah. So that's the end of our presentation. What I'm going to do is I will show you, this is the completed library, and eventually once you get it to train, OpenAI Gym actually has a really cool function where you can, on a certain state, you can actually render the environment. So let me show you. So it's called env.render. And basically what it allows you to do is actually view the environment moving. And you can leave it, it'll render, and then you can see what happens after you render the environment at that step. So if you're running our code, if you wanted to, after you trained your code for say a little while, you could put another loop under here that would allow you to render it and then watch what you've done actually work, which is super cool. And it's one of the really great advantages about using OpenAI Gym versus some other places. And there are more games than just Cartpole. They have the whole suite of Atari games that were originally used. They also have a couple of other more simple games, like one's called Lunar Lander, which is my favorite personally, where you're trying to get a lunar lander to land on the surface without breaking and destroying itself by controlling how slow it falls, which is super cool. And they have them both in discrete spaces like this algorithm, but other algorithms where it's continuous. So for example, say instead of moving the cart, you wanted to control how much torque was applied to the like axis or whatever. Imagine you had a motor there and you wanted to change how much torque was applied to the axle. And that would be continuous because unlike discrete where it's either going to be left or right, you could theoretically have any value as the torque, any decimal point value as the torque. So that's called a continuous action space. And DQN isn't built for a continuous action space. There are other algorithms that like DDPG and TD3 are two examples, and that probably sounds like nonsense, but there are a bunch of other algorithms out there that are suited for continuous action spaces. And if you're interested in that kind of stuff, again, reach out to us. We have a link to the original paper here that talked about DQN from the University of Toronto. And then there's also different policies like policy gradients. And that's like what I mentioned with finding continuous spaces and what Andrew mentioned about on policy versus off policy models. And so we have PyTorch docs, and we'll have these slides available for all of you. We'll throw them in the Git repository, and you guys can look at them whenever you feel like it. Andrew has some cool blog posts about reinforcement learning stuff. And then if you are really into this stuff, the book for reinforcement learning is from Sutton and Bartow, Reinforcement Learning. You can get the second edition. The second edition is the one you really want.
Yeah, don't get the first edition.
Yeah, the second edition handles the non-tabular stuff. So this is the book if you're really interested in reinforcement learning. Yeah, and like Peter says, you can find it for free online. That's the book if you're really looking to get into this stuff and if you're really looking to understand it. And yeah, that's it. If you have questions that weren't answered in this workshop, I knew we moved pretty fast and it's kind of a complex topic, and it took me a very long time just to understand the very basics. I still really don't understand the basics. But if you have any questions at all, feel free to hesitate. Feel free to reach out to either of us. Don't hesitate to reach out to either of us, and we'd be happy to help you if you want to work on your project or if you just have questions in general. And I'll open the floor now if there's anyone who has any questions. Alrighty, Andrew, you have any closing remarks?
Nah, that's all I got.
Alrighty, thanks. Yeah.
Yeah, thanks for coming. Hope you learned something.
Alrighty, see you guys.
See ya. Okay.
And stop recording.
You hit stop recording?
Yeah, I can.
Okay, cool. Stop recording.